Okay, so let's proceed with the next topic. We have so far covered the introduction to chapter 6, which is the second law of thermodynamics, and you have seen the definition of thermal energy reservoirs. We have the source, which supplies heat, and the sink, which absorbs or receives heat. Okay, and the important feature of the reservoir is that while it supplies and absorbs heat, its own temperature remains constant. Okay, so now we come to heat engine. Okay, so let's look at what it is first. Heat engine is a device that converts heat to work. Okay, so we need devices to do a lot of stuff, right? That's the nature of device. When we buy a device, when we create a device, we want it to do something for us. So that doing something is typically to do work. And as you know, work is motion. Alright, work is motion. So heat engine is a device that converts heat to work. The conversion of energy is basically first law. Okay, but you can't just take heat and then suddenly produce work. It doesn't happen that way because of the second law. Instead, normally when we do work, we generate heat. When you walk, the friction will generate heat. When the motor is turning, motor in a device, a fan or for example, it generates heat. So work typically generates heat. So what if we want to do the opposite thing? So look at the diagram here on the left. Rotating the shaft will increase the internal energy of water, U. And the heat will leave the water. So if you rotate this shaft, the energy of the water will increase. Energy in what form? Of course, we're talking about internal energy. Okay, it will increase, and then if let's say this is not an insulated system, the increase will cause an increase in temperature, and therefore heat will be transferred out to the surrounding. This is a natural process. It follows the first law, it follows second law. But what if you want to do the opposite? So you heat up the water, and then suddenly, magically, the shaft will turn. No, that's not going to happen, right? So we need the device like heat engine in order for this to happen. So characteristics of heat engine. They receive heat from a high temperature source. Okay, high temperature source can be solar energy, can be oil furnace, can be nuclear reactor, and like I said, the previous topic, it can be the sun. Okay, anything at all that can be considered as a thermal reservoir. So it will receive heat from that, and it will convert part of this heat to work. And normally when you talk about work, it's usually in the form of rotating shaft. Okay, it converts part of this heat. Yeah, that's a keyword here. Part of it, not all of it. And then what happens to the rest of the heat? They reject the remaining waste heat to a low temperature sink. Okay, so part of it becomes work. There's a remaining heat we call waste. Waste means something you cannot use anymore. Reject it to the low temperature reservoir or the sink. And finally, most important part, they operate on a cycle. So it's not a one-off process. It has to operate on a cycle for you to get continuous supply of work. Okay, so these are the characteristics of a heat engine. And in order for this to happen, for it to operate on a cycle, there has to be a working fluid. What is a working fluid? It's the fluid to and from which heat is transferred while undergoing a cycle. So there's a cycle. Just think about a system like your aircon system or your car. Okay, so all the devices are working. You can't just have one device. You need to have all the devices. In aircon, for example, you need compressor, you need the what do you call this? The pump. Okay, so how are these devices connected? So the working fluid is what connects them. Okay, so you will see in specific system what kind of working fluid are we referring to. Right, so that's the introduction to heat engine. Okay, so what you are seeing now here, the diagram on the left is a schematic diagram of the steam power plant. Okay, we're going to go to the diagram one by one, but let's look at the definition first. Steam power plant is an external combustion engine. What is external combustion engine? It means that the combustion is happening outside the cycle. Okay, combustion takes place outside the engine. Thermal energy released during this process is transferred to the steam as heat. Okay, so when you look at this diagram, the combustion is happening in the furnace. Okay, so the furnace is the source, energy source, the reservoir. And the sink is maybe just the atmosphere. So let's look at the entire system. So the plant is the whole thing. You see heat engine, it is the whole thing. It's not just one device. Okay, it's made up of different devices. Okay, so what happens at each stage? Let's see. Okay, first you ignite the furnace. So the furnace is on, it supplies heat, Q in. It supplies heat to the device called the boiler. So what happens in a boiler is, this is a steam power plant, therefore the working fluid is water. What happens when you boil water? It turns into steam, obviously. Okay, so at this process, amount of heat supplied to the steam in boiler from a high temperature source, that is Q in. Okay, so now you have nicely converted this water to steam. So it follows this path. Look at the arrow. Yeah, it goes into the turbine. What happens in the turbine? A steam has very high energy. What it does is it will rotate the blades in the turbine. Okay, it will rotate the blades in the turbine and produce work output. How? The blades in the turbine are connected to a shaft. So here there will be a shaft coming out of the turbine, normally connected to generator. But we don't touch that point. We just want to produce the work output. So a shaft, rotating shaft, considered work output. Okay, so work out is the amount of work delivered by the steam as it expands in the turbine. Okay, as it rotates the turbine blades. Okay, so what happens to the steam next? It exits the turbine, obviously, with different properties now. It has spent all its energy here. You've learned this in chapter 5. Turbine and compressor, remember? So turbine is opposite of compressor. So the pressure will be different, the temperature will be different as it comes out. So it comes out, it has to enter the device called condenser. So condenser, how to remember what it does? It condenses. Condenses means turning from steam to liquid. Condensation. or vapor turning into liquid. How to turn vapor into liquid? You cool it down. How to cool it down? Reject heat. Remove the heat. Okay, how to remove heat? Put it in contact with something that is colder. Let's say this is 50 degrees. This is 30 degrees. Automatically, heat will be transferred. Okay, so your steam coming out from the turbine will be condensed. So Q out refers to the amount of heat rejected from steam in the condenser to a low temperature sink. That sink can be anything, atmosphere or a river, etc. So it doesn't matter. At least not for us now to understand this theory, it doesn't matter. Okay, so after the condenser, the liquid now, okay, the liquid water has to go to the pump. Because there's some work in that needs to be supplied, amount of work requires to compress water to the boiler pressure. So the water that comes out from the condenser has low pressure. In order for it to complete the process and repeat the cycle, it has to match the pressure here. Comes out here low. This has to be this value. So how to increase pressure of water? Use a pump. Okay, so this is additional work required. The pump will increase the pressure and then you can send the water back to the boiler and the process continues. Okay, an important equation. I hope you write this down as you watch all these videos. The net work output produced is equal to, of course, work out minus work in. This is energy balance. Okay, the net work out minus work in. Or, this is also very important, write this down. In the case of this heat engine, you can write it as Q in minus Q out. Okay, so net work equals to, you can write it like this. So write this equation first under heat engine. This is how we can calculate how much work is being produced by the entire system. Okay, next we come to the thermal efficiency. Okay, any device has an efficiency. Okay, and the efficiency, the general equation, you see this, NTH means thermal efficiency. The symbol nu means efficiency. TH means thermal. Okay, so when you talk about heat engine, you're talking about the thermal efficiency. So generally, efficiency is desired result, or in other words, what you want over required input. Okay, required input is what you pay. Alright, that's a general equation for efficiency. What you want from the system or what you're getting from the system divided by what you have to pay to get it. So for heat engine, what do we want? Of course, you want work output. Okay, so we put that at the top, work output. That's the whole point of having a heat engine. What do you have to pay? You have to supply the heat source. So divided by what you pay is the Q in. So this is the equation for heat engine's thermal efficiency. Write this down as well. Okay, and it says here that thermal efficiency is always less than 1, or if you use percentage, always less than 100%. Always. Why? Why is it not 100% efficient? Because we have to reject heat. So there's still some waste. So the waste is causing the efficiency to be less than perfect. Okay, so if you look at this diagram, we have the same source. Source means heat source. We have the same sink that will absorb the waste heat, and then we have two different heat engines, 1 and 2. So the source supply the same amount of heat, 100 kilojoule. Heat engines 1 and 2, because they are different, they produce a different work output. This one produced 20 kilojoule only, this one produced 30 kilojoule. So what about the waste? The waste is as simple as the waste heat is 80. Because 100 minus 20, you get 80. And for the other one, 100 minus 30, 70. So which one is better? The one that produces more work. And it shows in the thermal efficiency. This is 30% efficient. This is 20% efficient. Okay, very simple. So this is calculated thermal efficiency. What you want here is the work output, 30 kilojoule. What you pay is 100 kilojoule, the Q in. Therefore, this is 30%. Very, very straightforward calculation. Okay, this is quite an important slide. So what can we do with the equation? So for heat engine, you've seen this. What you want, work output. What you pay is a heat supply. Okay, to make it simple, I'm going to lead you to this pink equation. So what happens here is we replace this portion with Q in minus Q out. You saw in the previous slide I asked you to write down Q in minus Q out equals to work output. So we can replace this. So what happens when you replace it? Thermal efficiency becomes Q in minus Q out over Q in. This equation becomes this. Q in minus Q out over Q in. And this can be written as 1 minus Q out over Q in. Okay, so same equation. One version, you can use it this way, you can use it this way. So in some cases, let's say you have to calculate, you don't have the work output. You have Q in and Q out, so you can use this version. What's most important, I suggest that you understand what it means. The efficiency is what you want. In a heat engine, what you want is the work output. What you pay is the heat source. So from that understanding, you can easily figure out how the equation should be. And of course, you have to also understand this. The same thing that we have here. This is how we get it from the energy balance equation. Okay, remember this. Understand what is efficiency and you can work out these equations. Okay, as this is a recorded lecture, you can pause anytime you want to write things down or whatever. So I'm just going to proceed. This slide will show you cyclic devices such as heat engine, refrigerator and heat pumps often operate between high temperature reservoir labeled as TH for temperature high and a low temperature reservoir at temperature TL. Stands for low temperature. Okay, so what does that mean? This is your heat engine. We have the boiler, we have the turbine, condenser, and pump operating in a cycle. As I said just now, this whole thing is considered one device. It's a system. So we have our source, heat source. It has to be at high temperature. That's why TH. This is not heat, this is high temperature. And then it produces work, fine. And then it rejects the heat at low temperature, TL. So this is your heat sink. Okay, so instead of calling it Q in and Q out, just now we said this is Q in, this is Q out. We are going to call it QH and QL. Okay, QH does not mean high Q and this is low Q. No, QH is the Q from the high temperature source. QL is the heat that is transferred to the low temperature reservoir. So the letter L and H refers to the temperature of the reservoir, not exactly the amount of the Q. Okay, don't get mistaken about that. So based on this diagram, efficiency, what you want is this part, so we write it at the top. What you pay here, what do you have to pay is QH. So that's your equation. So you see, if you understand, you can get different versions of it. So the net work output is, instead of Q in minus Q out, we write it as QH minus QL. Okay, QH minus QL. We're just replacing in and out with H and L. Okay, so the equation for the thermal efficiency, you can write it as 1 minus QL over QH. How do we get this? From this equation, we get this version. QH over QH becomes 1. Okay, so we get this one. You can use whichever version according to the suitability of the question later on. Okay, let's look at some examples of what kind of values of efficiency do we get from devices around us. Okay, ordinary spark ignition automobile engine, your normal car engine, is 25% efficient. Okay, not as high as you imagine, right? If it's a diesel engine, 40%. Large gas turbine plants also 40%. What is a gas turbine plant? Okay, means the plant operates with gas as a working fluid. Just now we saw steam was a working fluid. Okay, a 60% efficiency if it's a large combined gas and steam power plant. Okay, the power plant is in a large scale and it combines gas and steam as the working fluid. This has a higher efficiency. So what does that mean? These are not very good numbers. Almost 1/2 of the energy supply ends up in the rivers, lakes, or atmospheres as waste or useless energy, even for the most efficient devices. So this is efficient enough. Okay, this is actually very high in terms of device efficiency, but still only 60%. 40% of it goes to waste. Okay, so that is very typical. So I believe that's it for this topic. You've learned about the devices or the components in a heat engine, specifically a steam power plant, and you've looked at how to calculate the efficiency of the steam power plant. So I think now we can go through this one example. A steam power plant produces 50 megawatt of net work. Get used to writing it down. Megawatt, okay, net work. So even though it's called work, the unit is watt, so it has a dot. This is the work output. While burning fuel to produce 150 megawatt of heat energy at the high temperature. So you need to produce 150 megawatt of heat energy in order to produce this work output. So 150 is the QH here. 150 megawatt coming from the furnace. Determine the cycle thermal efficiency and the heat rejected by the cycle to the surroundings. Heat rejected, QL here. Okay, very simple question. Thermal efficiency, we have this equation. What you want in the heat engine again is the work output. I should put a dot there. What you have to pay is the heat source, heat supply. Put it in 33% or 33.3%. This is the efficiency. Okay, the next part is heat rejected, QL. So what equation do we have? Work output is equals to QH minus QL. Very simple. You can add the dot here to show that you're talking about rate. Okay, so QL is just 150 minus 50, 100 megawatt. So 100 megawatt is being rejected. Okay, very straightforward application of the equations. Okay, another one. Heat is transferred to a heat engine from a furnace at a rate of 80 megawatt. From furnace, so that means this is the source. Okay, so not always that you have a diagram like this, so you have to know how to place all these values. If the rate of waste heat rejection to a nearby river is 50, obviously this is QL. Determine the net power output, work output, and the thermal efficiency. Okay, so you have QH and QL. You can obtain work output very easily. Just use this equation. Work output, QH minus QL. Okay, and once you have the work, you can calculate efficiency using this equation, get 37.5.